So, what are conservative forces? Conservative forces are forces where the work done in a closed path is zero. In a closed path or a closed loop is zero by the conservative forces. Or in other way around, we can say that if the work done in a closed path is zero by a force, I mean every time, then the force is obviously conservative force. Now, so here, say consider a closed path. So that's a closed path. And suppose so F is a conservative force. So that is F and a small length of the path vector dl. Okay, so this f dot dl work done in this small displacement dl. Now you integrate it, so along the closed path. So you give this sign, this round sign means it is the closed integral. That means it is dl. Then again take dl, like this, and there are these forces also. Somewhere it is like this, somewhere like this, somewhere maybe like this the force. So you go on adding this f dot dls, and after that you end up at this starting point where you have started. You end up here, right? So then the closed integral, this is known as the closed integral, so that is equal to 0. Then f is a conservative force. Now in this, so in the other way we can say that work done by conservative forces is path independent. Now we will prove this statement that work done by that means you can define conservative force in this way, what we have done, that work done by, so if the work done in a closed path by a force is 0, then it is conservative force. In other way you can say work done by conservative forces is path independent. That means if the work done by a force is path independent, then also you can say that the force is a conservative force. Now we are going to prove. So here consider the 2 points or 2 states 1 and 2. Right, 1 and 2 are the states or points. And there are 3 paths here given by path 1 and path 2 and path 3. This is conservative forces around. So path 1, path 2 and path 3. Path 1 is from 1 to 2 actually, as you see, path 1. Path 2 is also from 1 to 2 and path 3 is from 2 to 1. Now, you know, for conservative forces, integral f dot dl is equal to 0 implies, say, for first we will consider for this loop comprising of path 1 and path 3. Consider the following loop. having path 1 and path 3. So here integral of 1 to 2 f dot dl along path 1 plus integration from 2 to 1 f dot dl, this is via path 3, is equal to 0. Now again consider the following loop consisting of path 2 and return via path 3. Now these are points 1 and 2, here also points 1 and 2. So here also the closed integral is 0, so we can write 1 to 2 f dot dl via path 2 plus 2 to 1 f dot dl via path 3 is equal to 0. Now if you name this equation 1 and equation 2, from equation 1 and 2, what do you get? From equation 1 and equation 2, you can equate one term here actually, this so integral of 2 to 1 via path 3, integral of 2 to 1 via path 3, this is common, so you can equate. So from this we can conclude that integral of 1 to 2 f dot dl via path 1 is equal to integral of 1 to 2 f dot dl via path 2. So this proves that as say points 1 to 2 and say path 1, now you can forget about path 3. So integral f dot dl from 1 to 2 via path 1 is equal to integral of 1 to 2 f dot dl via path 2. So this is actually work done, right? Work done by force F in path 1. Force in path 1, and this is work done by the force in path 2. So it does not depend whether it is path 1 and path 1 or path 2, provided it is between the same points 1 and 2, right? So we can say that, okay, in a conservative force field, that means field means a region where there are conservative forces only, or the domain of the conservative forces in a conservative force field, this work done from 1 to 2 can be defined as, can be expressed as difference between two functions, say phi 1 minus phi 2, where this phi 1 and phi 2 are two constants, are the constants associated with points 1 and 2, points or states, whatever, points 1 and 2 in the conservative field. So as the work done from 1 to 2, is this integral f dot dl from 1 to 2 is not dependent on path, so I am not mentioning the path here, can be expressed. So this depends on the points 1 and 2 only. So we express it as the difference between these two constants. The constants, so they have dimensions. So the dimension of phi is that of work, right? Because work minus work, or work or energy, same thing. Work and energy are having same dimensions. So this phi is known as potential energy. That is how we define potential energy. So here phi 1 is potential, so in short form you write as PE. Phi 1 is potential energy for state 1, point 1 or state 1, and phi 2 is potential energy for state 2. That means in a conservative force region, if you have points 1 and 2 or states 1 and 2, then the work done obviously by conservative forces from 1 to 2 is expressed as phi 1 minus phi 2, right? So these phi 1 minus phi 2 are phi 1 and phi 2 are constant. So a point where, or a state, or a point where the value of phi is 0 is known as the reference position. So what matters is the difference in phi, not the absolute value of phi. You can call this phi as U also, U for potential energy. So all these things represent potential energy. U or phi, you can write it like PE also. So W1 to 2 by conservative forces is U1 minus U2. A simple example I will give you. Say this a ground and there is a ball of mass m. So the gravity force on the ball is coming this way down, mg. Now say consider this point as 1 and the point on the ground as 2. So work done by gravity, the height is given as h. So work done by gravity when the body falls from 1 to 2, I mean falls through a height or shifts from 1 to 2, is this W1 to 2 by gravity. So mg multiplied by h, right? Because this is the displacement is h. So you it's phi 1 minus phi 2 or u1 minus u2. Okay, now we can choose our reference point. So that is that we can choose the reference position. Say here we choose 2 as reference. That is, what is u2 or phi 2? That's equal to 0. Therefore potential energy at state 1 equal to u1. So is given by, now look at this equation. Here in place of u2 we will put 0. So that is given by mgh equal to u1 minus 0, implies u1 is equal to mgh. So it depends on the reference position. Okay, I am showing it with gravity, that simple constant gravitational force, because we are used to with this equation, right? That is why. And you know also work energy theorem, that is also true in all cases. So what was the work energy theorem? Remember it? It says that work done by all forces is change in kinetic energy. Work done by all forces is change in kinetic energy. Now consider two states or 2 points 1 and 2 in conservative force field. That means all the forces are conservative forces. So that's 1 and 2, and the body is shifted from 1 to 2. Body shifted, or system is shifted from 1 to 2. States 1 to 2. That is it's not necessary that a body always has to shift from 1 to 2. Maybe it's the deformed state of a spring. We will learn later on. Spring potential energy. By the way, the simple example is that of a body or a particle which is being shifted from point 1 to point. Consider two states 1 and 2 in conservative force field. Body shifted from 1 to 2. So work done by conservative forces is W1 to 2 equal to, by work energy theorem, is kinetic energy at 2 minus kinetic energy at 1, right? That is K2 is kinetic energy at state 2 and K1 is kinetic energy at state 1. Now that is true from work energy theorem, this equation. That's okay, but we have defined also potential energy by definition of potential energy, PE. So for conservative forces, this work done from 1 to 2 is phi 1 minus phi 2, or U1 minus U2, or PE1 minus PE2. Right? PE is potential energy at state 1, PE2 is potential energy at state 2. So therefore we can equate. We can, from these two equations, we can reach at a conclusion that that's kinetic energy at state 2, Ke2 minus Ke1 equal to Pe1 minus Pe2. So that means kinetic energy at 1 plus potential energy at 1 equal to kinetic energy at 2 plus potential energy at 2. So this happens, so this equation is true if there are conservative forces only. There are only conservative forces around, then this expression is true. Now for non-conservative forces, the work done in a closed loop is not 0. Is not equal to 0, that means For non-conservative forces, integral of F dot dl is not equal to 0. So same way we can say, in similar way we can say that, in other way we say that for the non-conservative forces, work done is path dependent. So in this example, both conservative and non-conservative forces are present in this region, and the 1 and 2 are the initial and the final states of the system, or any two states of the system, or you can say the particle or the body is taken from point 1 to point 2. Then we can write kinetic energy at 2, say for the Ke1 is kinetic energy of the body at 1, or the system you can say as a, in general, Ke2 kinetic energy of body at 2. Now Pe1 is potential energy at 1 of the body rather, or the system. Pe2 is potential energy at state 2. So now from work energy theorem, so we can use here work energy theorem, that is general, that that does not depend on whether the forces are conservative or non-conservative. It works for all. So the work energy theorem, according to work energy theorem, what do you have? Work done by all forces, work done by all forces from 1 to 2 is equal to kinetic energy at 2 minus kinetic energy at 1. So we can break it up, work done 1 to 2 by conservative forces plus work done from 1 to 2 by non-conservative forces, that's equal to Ke2 minus Ke1. Now by definition, work done 1 to 2 by conservative forces, that is by definition a difference in potential energy, P1 minus P2. So therefore we can arrange the terms in the equation like that. So that's Pe1 minus Pe2 plus right here W non-conservative from 1 to 2, this same term, right? This, instead of writing the bracket in non-conservative, here I have written the bracket. This is the same term, right? This term and this term. Okay. So equal to Ke2 minus Ke1. That is, we can bring it to one side, Ke1 plus P1 total energy, kinetic plus potential, plus W non-conservative from 1 to 2 equal to final total energy, Ke2 plus P2. So this is the expression. This is the general expression we will use in presence of both conservative and non-conservative force. If there are no non-conservative forces, then this term will be 0. Else, this is the most general form in which you can use the work energy equation, and this is the most helpful equation to solve problems.